Hey everybody, welcome back for the Chapter 6 lecture. This time we're talking about the language of chemistry. Now, word to the wise, if Chapter 5 with the negative and positive ions did not make sense to you, you're going to want to pause on this and get that together, because you're going to need to know about negative and positive ions for naming and writing chemical formulas, which is the language of chemistry. So again, if that is something that's difficult for you, you're definitely going to want to get that reinforced. So send me a message through Blackboard course messages, get somebody else to help you out, maybe study together virtually. Look at the YouTube video again for Chapter 5, something. Because you need to understand those negative and positive ions to move forward. Not for the whole thing, but when it comes to writing chemical formulas, you're going to be lost. So make sure that you understand the ions portion of Chapter 5 before you move on to all of Chapter 6. With that said, let's get going. So we're talking about the International Union of Pure Applied Chemistry. They have a set of rules for naming compounds. These are the rules that we are using in this class. Yes, there are other naming rules. We're not talking about those. They're valid, but for the purposes of this class, in terms of assignments and exams, only the naming rules that we've covered are going to be considered correct. So when it comes to your homework on Mastering Chemistry and your Chapter 6 check-in, make sure you don't just Google it, because Google will tell you the wrong answer. If it doesn't come from the rules that we used in this lecture and in your textbook, it will be considered wrong. So make sure that you're using the rules from this textbook. All right, now that we've got that public service announcement out of the way, let's get going. In order to name, you have to be able to classify compounds. We're going to talk about inorganic compounds, and by and large, they don't have the element carbon in them. There are some exceptions like carbon dioxide and carbonates. They have carbon, but they're inorganic compounds. This flow chart gives you some organization of how compounds can be broken up. So the three major classes that we're going to talk about are ionic, molecular, and aqueous acids. Each of those can be broken down further, and we're going to talk about the 5 common classes. So the classes that you're going to need to know for this class are binary ionic, and I'll write down my abbreviations for them. So you may want to jot this down in your notes, because I use abbreviations. It's just too many words. It's going to double the length of the video if I write it out every time, okay? So binary ionic compounds, BIC. Ternary ionic compounds, TIC. I'm sure that you're getting the pattern here. Binary molecular, BMC. Binary acids are BA, and ternary oxyacids are TOA. These are the 5 classes that we're going to learn how to name and write chemical formulas for. First, we're going to go over naming. We're going to start with the ionic compounds because they're pretty simple. Binary means 2. So for a binary ionic compound, you're looking for a compound that contains 2 elements. It's always going to have 1 metal and 1 nonmetal. So here are 2 examples. We've got table salt, which is sodium chloride. Sodium is the metal. Chlorine, that's the nonmetal. If you don't remember the periodic table in terms of which elements are metals and which ones are nonmetals, you're going to want to revisit Chapter 4. We talked about that when we were talking about sort of the trends of the periodic table and just breaking down the periodic table a little bit in chapter 4. So we talked about metals, nonmetals, and metalloids. You're going to want to refresh yourself on the metals and nonmetals. Likewise, in the second compound, we've got a metal and a nonmetal. So these two compounds are binary ionic compounds. Before you can name, you have to be able to classify. So we're building up to naming. For ternary ionic compounds, you're looking for 3 elements. You're always going to have a metal plus some nonmetals. I'll give you a slightly better definition of the ternary ionic compound later on. We have to cover a couple of other things first. But for now, just know that you're going to be looking for, by and large, a metal plus nonmetals. And you want a total of 3 elements. In this first one, we have the metal, potassium. And then we've got 2 nonmetals, nitrogen and oxygen. There are 3 oxygens here, but we don't care about that. What we care about is that there are 3 different elements, not how many of each element, but that there are 3 elements. And likewise, there are 3 elements in this second example, the aluminum, and that's the metal, and the nitrogen and oxygen are nonmetals. Moving on to the molecular compounds. The only one that we're covering are the binary molecular compounds. Again, we see the word binary, so that means 2. You're looking for 2 elements, and they're both nonmetals. Examples of that would be ammonia, which you may know the smell of that. Cleaning solutions sometimes have ammonia in it. And water. Water has hydrogen and oxygen. Those are both nonmetals. The final group that we're going to look at is aqueous acids. Binary acid, again, tells you that you're looking for 2 of something, and it contains 2 elements. There's always going to be a hydrogen plus a nonmetal. The other clue that you have in acid is that in parentheses, you're going to see the AQ for aqueous. So that tells you you have an acid. You just have to figure out if it's a binary acid, which has the hydrogen plus a nonmetal, or if you have a ternary oxyacid. Ternary, again, means 3. And for this, you're going to have a hydrogen plus oxygen plus some other nonmetal. You will again see that aqueous in parentheses. So there are 3 elements in the ternary oxyacid. Let's practice classifying. And we're going to do plenty of practice in class. But I want to show you the kind of logic that you're going to need to use when you're going through and classifying these compounds. If you can't classify the compound, then you won't know which naming system and rule to use. So this is a very crucial point. For the first compound, we see a metal plus a nonmetal. We see 2 elements. So that tells you that you've got some kind of binary something. And our only choices for binary are binary ionic, binary molecular, and binary acid. Binary molecular has 2 nonmetals, so it can't be that. And it's not an acid because we don't see that aqueous and we don't see a hydrogen. So it has to be a binary ionic compound. For the second compound, we see 2 nonmetals. there's two of something, and they're both nonmetals. So it's got to be binary, and the only thing that has just nonmetals, and we're not talking about any aqueous anything, binary molecular compound. The third compound has a metal plus two nonmetals for a total of 3 elements. So right off the bat, we're talking about something that's ternary. The only two options are ternary ionic compound or ternary oxyacid. You don't see anything that indicates an acid. There's no hydrogen, there's no aqueous. So it has to be a ternary ionic compound. Finally, we see a hydrogen plus a non-metal for a total of 2 elements. We also see this aqueous here. Since there's only 2 things, it's got to be binary. And we see the aqueous, so that means it's got to be a binary acid. So that's just an example of how you can walk through the different types of compounds and reason through which compound type you're looking at. You will need to be able to do this in order to name compounds. So if you can't classify, you can't name properly. This chapter builds each concept, one on the other, up to naming and writing chemical formulas. So if there's any part of this that you have a problem with, you need to address it right away, because the rest of the chapter will not make sense. So we classified compounds, inorganic compounds. Now we're going to classify ions. Remember from chapter 5 that an ion is just an atom or a group of atoms with a charge. They can be positive or negative. A positively charged ion is a cation. A negatively charged ion is an anion. If you have a group of atoms with a negative charge, then it's a polyatomic anion. Where poly, we're just talking about more than one. Just like with classifying compounds, we can make a flowchart to show the different categories of ions. So the 2 major categories, which we just covered, are cations and anions. But each of those can be broken down into monoatomic and polyatomic. Monoatomic means one atom. And the poly means many, or at least more than one, okay? And it's the same thing for the anions. We're going to start with the monoatomic cations. At the end of chapter 5, we talked about positive ions and the fact that metals, when they're participating in chemistry, they lose their valence electrons to form a positive ion. Those positive ions are called cations. When you're naming a cation, it's quite simple. You look at the symbol for the parent atom. So in this case, we're looking at Na, that's sodium. So you write sodium. Then you follow it with the word ion. For magnesium, Mg is magnesium, you write that out, followed by the word ion. So this is monoatomic cations. And all you're doing is the name of the atom plus the ion. That's how you name those. When we're talking about figuring out the charge for a monoatomic cation, again, this should be review. The metal ions from the representative elements, meaning the ones that have the A after them, the group number is equal to the charge. So if you're a group 1A metal, then you have a +1 charge. If you're in group 2A, you've got a +2 charge. Again, this is only for metals because metals form cations. Now, of course, there are some exceptions. In group 4A, lead and tin can form multiple ionic states. They can form a 2+ and a 4+ ion. Also, there are lots of transition elements, and they can have more than one ionic charge. Most of them will form a 2+ ion, but they may also lose more than just those 2s electrons to form different ionic charges. So we have to have a way of differentiating between these different ions when we're writing names for compounds. One system that you can use that I prefer is the stock system. What you do is you write out the name of the parent atom, just like before, but then you're going to write out the charge as a Roman numeral in parentheses. What that does is it tells the person who's looking at the name of the compound what charge that copper is, because it can have multiple charges. And then, of course, if you're just talking about the ion, you follow it with the word ion. So copper 2+, you write the copper, which is the name of the atom, and then the 2 in Roman numerals in the parentheses, followed by the word ion. Now, if you don't know your Roman numerals, that's okay. I will give you some. There's 1, 2, 3, 4, 5, and 6. And of course, again, there are exceptions. We said many of the transition metals can form multiple cations. Not all. The exceptions you'll need to know are zinc, silver, and cadmium. They only form one cation. So you do not need to use the stock system for these because there's only one ionic state. There's another system called the Latin or the suffix system. And this uses "ic" or "us" to designate the charge. For the cation with the lower charge, you give that the "us" suffix. The one with the higher charge gets the "ic." So this is an older system. You will still see it on some chemicals. If you look it up in Google, you'll still find things named this way. But it's not as descriptive. All it does is tell you which one is the higher charge and which one is the lower charge. It doesn't tell you what the charge is like the stock system does. For our purposes, you will need to know this for your assignments, but for the exam, I'm going to focus on the stock system. Let's practice naming. So if you want, you can pause this and try to name these cations. Otherwise, you can just follow along and look at the logic for how I do it. When I see an ion, I first figure out, is it a metal or a non-metal? Aluminum is a metal. Then I figure out where it is. Aluminum is in group 3A. That means it's not a transition metal. So I can figure out its charge and double check. Okay, it's in group 3A. It's 3+. Great. For naming this ion, all I have to do is write the name of the parent atom, which is aluminum, followed by the word ion. For the second one, again, we're looking at a metal. And I'm going through this because I know we're saying, well, duh, we're naming monoatomic cations. So aren't they all going to be metals? Yes. But on your homework or on an assignment, I won't tell you, please name these monoatomic cations. You're going to have to figure that out yourself. So this step is crucial if you don't know what you're naming already. We're naming a metal. When you look at where zinc is, it's a transition metal, which I abbreviate TM. Transition metals can sometimes have more than one charge. So now you have to ask yourself, is zinc an exception? Yes, it is. It only has one charge, which is 2+. So when we name this ion, it's going to look very similar to the one that we just did. Write the name of the parent ion, or the parent atom, followed by the word ion. There you go. The third one, again, it's a metal. Big surprise. It is also a transition metal, but it's not an exception. That means that we should use the stock system. And all that means is we have to write the charge as a Roman numeral in parentheses after we write the name of the parent atom. So you write out chromium. Then you write 6 as a Roman numeral in parentheses, followed by the word ion. So that's naming monoatomic cations. Let's move on to the monoatomic anions. Again, we covered these at the end of chapter 5, not the naming part, but how to make an ion and what electrons are lost or gained. With monoatomic anions, we're looking at nonmetals. And specifically, we're looking at groups 5A through 7A. All of those nonmetals in those groups will form monoatomic anions. And they do so by gaining valence electrons. The way that you name these is by getting rid of the end part of the name and writing in IDE. For example, Br-, that comes from the element bromine. We're going to keep that first part, the first syllable, get rid of the last part of the word, and replace it with IDE. Then you write the word ion. And that's how you get the name bromide ion. Same thing with nitrogen. If we start with nitrogen, we're going to keep the root of the name, which is usually like the first syllable-ish. Get rid of everything else and replace it with IDE. Then you write the word ion afterwards, and that gives you nitride ion. So this is a good table to double check your work as you're getting more comfortable with naming. You will not have access to this chart when you are doing your exam. To find the charge of an anion, you're going to take the group number, the one that ends in A, and subtract 8. That should be review. So if you have a group 5A nonmetal, its charge is going to be 5 minus 8, which equals -3. Again, that should be review. So if it feels like that's coming out of left field, you need to review Chapter 5. This table has some elements and their common charges. You will not have access to this during the exam either. You will just need to know the rules. You'll be able to figure out the charges for the transition elements. I'll show you how to do that, so you don't have to worry about memorizing those, except for these exceptions. You're going to want to know those. Let's go on to polyatomic anions, which I abbreviate PAA. They generally have oxygen combined with them, and those are called oxyanions, but there are some that do not have oxygen. A lot of these oxyanions have ATE at the end. So NO3 minus, that is the nitrate ion. SO4 2 minus is the sulfate ion. But there are some outliers. Hydroxide and cyanide end in IDE. So that still tells you that it's an anion. They just don't have the 8 like a lot of the other ones do. You will have access to the Common Polyatomic Anions chart. You'll notice that there is one polyatomic cation, and that is ammonium. All the others are anions, and there are 2 rows. You get the chemical formula in the first row, and then the name in the second row. So all of these ions you will not need to memorize, but you do need to be familiar with them so that you're not staring at this chart for 10 minutes to work on one problem. I'd recommend that you print it out and put it in your notebook. But it will be a part of so you'll have the periodic table and you'll have the common polyatomic ions for your upcoming exam 3. Let's talk about the naming of these oxyanions. So I mentioned that some of them have the ATE at the end. Others have ITE. So we've got the nitrite and the sulfite. Well, NO3 minus was nitrate. NO2 minus is nitrite. The difference is that the nitrate has 1 more oxygen than nitrite. And that's the difference between these 2 suffixes. 8 has 1 more oxygen than the ite. The other way you can say that is ITE has 1 less oxygen than the 8. Whichever one makes the most sense to you and sticks in your brain, that's the one you should go with. So let's go through another example. We have the sulfite ion, which has 3 oxygens. If we want to write the sulfate, ATE, that means we need to add 1 more oxygen for SO4. The charge on the ion stays the same. So the only difference is the number of oxygens. Let's do another example. The formula for chlorate is ClO3 minus. What is the formula for the chlorite ion? So 8 is ClO3. Ite should have one less oxygen. So instead of 3, it has 2 oxygens, but its charge is still the same. More naming. Ooh boy, I know. There's no math here really, but it's just a lot of rules to remember. I promise that with practice, it'll get easier. We have all the information that we need at this point in time to name ionic compounds. So we'll start with the binary ionic compounds. When you name these, you're going to combine the cation name and the anion name and smush them together. So the first part of the ionic compound is always going to be the cation. If we were just going to name the cation, it would be the magnesium ion. It's in group 2A, so that means it's not a transition metal. We don't have to do anything special. You just write the name of the parent atom, which is magnesium, followed by the word ion. Then we look at oxygen. If we were going to name that anion, you'd start with the atom, and then you get rid of everything after that root. So ox is like the first syllable, that's the root of the word. And you replace it with IDE, followed by ion. Then you're going to want to get rid of the word ion in both cases and smush them together. So the name of this compound would be magnesium oxide. Let's do another one. Our cation is mercury. Mercury is a transition metal. It's not one of our exceptions, so that means it's got multiple ionic states. And we can't tell just from looking at this right off rip what the charge of the mercury is. We first have to figure out the charge of the anion. We're dealing with sulfur. It is a group 6A nonmetal. That means that we find its charge by taking its group number, 6, subtracting 8, and that gives us -2. So the anion that we're naming is S2-. We take the root, which is sulf. We add IDE, followed by the word ion. Now let's go back to the mercury. This compound is a neutral compound, which means the charge is 0. If there's a 2- from the sulfide ion, then the mercury must be 2+. Because the charges have to cancel out. The way that you write this using the stock system is you write the parent atom name with the charge as a Roman numeral, followed by the word ion. You get rid of the word ion in both cases, and you slap them together. So this compound is mercury 2 sulfide. So we've taken the chemical formulas of binary ionic compounds and written the names. Now we're going to go in the reverse. We're going to take the name and write the chemical formula. Again, remember, we're looking at an ionic compound which has a positive ion and a negative ion. The formula, or the formula unit, is the simplest representative particle of that ionic compound. So it's got to have a neutral charge. It's the total positive charge from the cation that's equal to the total charge of the anion. So the positives and the negatives have to cancel. So let's practice. Here we have potassium bromide. Potassium is your cation. Bromide, that's your anion. You look up potassium on the periodic table. Its symbol is K, and it is a group 1A element, which means that we can figure out its charge just by looking at the group number. Its charge is +1. Bromide, well, the root for that is brom, which means that it comes from bromine, and its chemical symbol is Br. We find bromine on the periodic table, and it is in group 7A. For anions, monoatomic anions, you take that group number and subtract 8 to find the charge. In this case, we're doing 7 minus 8, which equals 1. So bromide has a negative charge, just -1. So if our potassium ion has a +1 charge and our bromide ion has a -1 charge, that means we're neutral. It all cancels out. So our formula is KBr. I want you to take a second and try this one. This is barium chloride. If you don't feel comfortable pausing it and giving it a shot, that's okay. We'll do practice in class. But you're really going to want to just jump in and just do it. The only way to learn with naming and writing chemical formulas is practice. There's literally no other way. You can memorize the rules, but you have to practice going through them and having a systematic method of stepping through classifying and naming each compound. The way that I'm showing you is just the way that I do it. But there are other ways, so feel free to find other ways that help you as long as it's the same naming system that we're using. Okay, back to the lecture. So barium chloride. We know it's a binary ionic compound. The cation is first. We're looking at barium. We don't see any Roman numerals or anything like that, so we don't need to worry about it. We don't need to say, oh, we need to use the stock system and kind of undo that, right? We just find barium on the periodic table. Its symbol is Ba, and it's in group 2A, which means its charge is 2+. The chloride anion has the root chlor, which comes from chlorine. Chlorine is a group 7A nonmetal, just like bromine. And it also has a -1 charge. Our cation is +2. Our anion is -1. That's not equal. So we've got to do something about that. What you do is find the lowest common denominator. And in this case, it's 2. So if we have one barium ion and two chlorine or chloride ions, then we'll have +2 and -2. And that is a neutral compound. The other way that you may see that done is simply by looking at the charge of the cation becomes the subscript for the anion. And the charge for the anion is the subscript for the cation. And since it's only one, we don't write the one in. It's doing the same thing. It's just that formally, you're finding the lowest common denominator. But that's just an easy trick and an easy pattern to follow. Let's write a formula for chromium 2 nitride. Right away, you know that chromium is a transition metal because it's got a 2 in parentheses. We don't even need to look at the periodic table unless you need to know what the symbol is for chromium, because we already know what its charge is. 2. We're told right there. Nitride, that comes from nitrogen. It's a group 5A nonmetal. For finding the charge, we're going to take that 5 and subtract 8 to get -3. So we've got +2 here, -3 here. Very much not equal. Lowest common denominator is 6. So that means we need 3 chromium 2 ions and 2 nitride ions. Again, look at the 2+ on the chromium, and there's a 2 as the subscript for the nitride. We've got a 3- for the nitride and a 3 for the subscript for chromium 2. This is probably the trickiest type to write a chemical formula for. But if you take your time and you use the same methodology every time, with practice, it will become very easy. Let's move on to ternary ionic compounds. It's still the same general process where you name the cation and then the anion. The difference here is that you need your polyatomic anion sheet. So that chart that I told you will have available to you with all the 8s and ites, you're going to need that. First thing you do is you name the cation. We've got a K, that means potassium. It's in group 1A. So that means for naming, all we have to do is write the name of the parent atom, potassium, followed by ion. For this ClO2, you need to find that on your chart. It is the chlorite ion. Just like before, you get rid of the word ion and smush them together. So that is potassium chlorite. In our second example, we've got cobalt. Cobalt is a transition metal. So we don't know right away what its charge is. we first have to look at the anion. Use that chart, look up ClO3, and you'll see it's the chlorate ion. Also, if you look at the ClO2 from above, that's chlorite, you add one more oxygen, that's the 8 form. It's just a throwback to earlier in this lecture. The chlorate ion has a charge of -1. However, there are 3 of them, which is what that 3 on the outside of the parentheses means. So that means our total negative charge is -3. In order for us to have a neutral compound, our total charge from the cation has to be +3. The way that we name that with the stock system is cobalt with the 3 as a Roman numeral in parentheses, followed by the word ion. You get rid of the word ion and smush them together. And the name of that compound is cobalt 3 chlorate. We know how to name. Now we need to go from the name to the formula. Again, you're going to want that polyatomic anion sheet handy. Let's take calcium nitrate. Calcium, its symbol is Ca, and it is a group 2A metal. Since it's not a transition metal, we can just use the group number to figure out the charge. 2A, that means it's 2+. Nitrate, you're going to look up on your chart. It's NO3-. So for our charge, we have +2 for the cation side and -1 for the anion side. That's not balanced. So our lowest common denominator here is 2. So you're going to have 2 nitrates. The way that you write this is the calcium, and then in parentheses, you write the nitrate, NO3, and outside of that parentheses, you're going to put how many you have, which is 2. Notice that the 2 in the charge of the calcium is now on the outside of the parentheses for the nitrate ion. Since there's only a -1 for the nitrate, we don't write a 1 here. But you can just imagine a 1 if you'd like, if it makes you feel better. Now let's write a formula that has a transition metal. We know it's a transition metal because we see the Roman numeral. So we don't even have to go to the periodic table. We're already told what this cation is. Iron is Fe, and because there's a 2 in parentheses, it means that the charge is 2+. Phosphate, you're going to go to your chart and find it, and it's PO4 3-. Word to the wise, you really need to be careful when you're writing down something from a chart, or you're, doing your work and carrying along a bunch of different lines of stuff. Make sure that you keep your work tidy and neat, and that you're not introducing errors. So if you write PO4 3- and then you write it again as 2-, and you carry the 2- through, you're going to get the wrong answer. So be careful. Stay alert and make sure that you double check your work. Take the extra minute and double check it, because it really can be the difference between a poor grade or a failing grade and a really good grade. Attention to detail is usually the biggest issue when it comes to chemistry. Not ability, paying attention to detail. So be careful, you guys. Watch everything. Back to the chemistry. So we've got our two ions here. Iron 2 plus. So that means our total for the cation is +2. And phosphate is 3 minus. Those aren't the same. Our lowest common denominator is 6. Which means we need to have 3 of those iron 2 ions. And in parentheses, we're going to write PO4 followed by a 2 on the outside. The 2 in the charge from the iron ends up outside of the parentheses for the phosphate. And the 3 from the phosphate ends up down there as the subscript for the iron. So if you see that pattern, then you don't necessarily have to go through this step here. But that just shows you what you're doing by using that pattern. So that's the ionic compounds. We did the binary ionic and ternary ionic. Now we're going to move to the binary molecular compounds, which are molecular compounds. As a reminder, these compounds have 2 nonmetal elements. And a molecule is the simplest representative particle of a binary molecular compound. For naming, you're going to first name the first element in the compound. So let's say you had CO2. The first element is carbon. There's only one carbon, but in this case, we're not going to use a prefix. For the first element, and I have this on the next slide, for the first element, if there's only one, you just write the element name. You don't need to use a prefix. For the second element, you're going to replace the end of the word with IDE, just like you do for the monoatomic anions. So we have the element oxygen. You're going to save the root, get rid of the rest, and replace it with IDE. Then you're going to add in a prefix that tells you how many oxygens you have. And there are 2. So the full name is carbon dioxide. I'm not going to give you these prefixes. Most of them you already know from math. If you don't know them, then you're going to need to know them. But I am not giving this to you for the exam. As I said, there's an exception. If there's only one atom of the first element, you don't use mono. But you will use mono if there's only one of the second element. So like in carbon monoxide, there's 1 carbon and 1 oxygen. But see, you use mono only for the oxide. Let's try naming a compound. You deal with things in order. We see a 4 down there as the subscript. 4 is tetra. And since we're naming the first element in the compound, we just write the name of it, which is phosphorus. For the second part, we again look at the subscript. That's a 3. The prefix we use for 3 is tri. The root of this atom name is sulf, because it's sulfur. So we're going to take that SULF and add IDE. That's as complicated as it gets. Those are binary molecular compounds. Let's try another one. If it makes sense to you, then I'd recommend pausing and trying to name this one for yourself. The first element that we see is carbon. We don't see a subscript, so that means there's only one. Since it's the first element, we don't use mono. You just write carbon. For the second element, there's 4 of them. The prefix for that is tetra. Cl is from chlorine, so the first syllable is chlor. We're going to replace the rest of that word with IDE. The full name is carbon tetrachloride. Now we're moving on to the acids. This is the last portion, so we have to name them and then write them from the formula. Or no, naming is writing them from the formula. So then we have to write the formula from the name. And we have to do that for the binary acids and the ternary oxyacids. Then we're done. So hang on tight. Remember that a binary acid has a hydrogen plus a non-metal. That hydrogen is always going to be first in the formula. You'll also see that AQ in parentheses afterwards. The way that you name these acids is by using the prefix hydro before writing the stem or that first syllable of the nonmetal. Then you sandwich that between IC and write the word acid. So HF, you would write hydro. The first syllable of fluorine, which is the parent atom, is fluor. Sometimes I write it backwards and write flower. You're not alone. It's okay. Then you follow up that root with IC, and write acid. If we have HI, it's hydro. The parent atom is iodine, so we're going to keep the first syllable, iode, and follow it with IC. Then you write the word acid. Hydroiodic acid. Let's do one more example. Start with hydro. Br is bromine. We're going to keep the first syllable, brome, and replace the rest with IC. Then you write acid. And again, I'll remind you, you're not going to be told that the compound is a binary acid or a binary molecular compound. It's simply going to be name this compound or write a formula for this, chemical name. You're not going to be told what the classification is. So you have to remember hydrogen plus a nonmetal is a binary acid. So you do that step first, and then once you know what you have, you move on to, okay, binary acids are named by using the hydro and then the root, and then ic, followed by acid. So it's a multi-step process. We're just focusing on those steps in two different areas. We talked about how to classify, which is is it a binary acid or whatever, in the first part of this lecture. Now we're doing the naming and writing chemical formulas, but all of those things go together. So just remember that. Now we've got to talk about ternary oxyacids. We're talking about those polyatomic anions, which most of them are oxyanions. The ternary oxyacids are made with hydrogen plus an oxyanion. So that is a ternary oxyacid. If the acid is made with an anion that ends in ATE, then you change that suffix to IC and add the word acid. So here we've got HNO3, and it's aqueous. If we were classifying this, we would see, okay, we've got a hydrogen and we see aqueous, so we know it's an acid. And since we see two nonmetals, which looks like an oxyanion, it has to be something ternary, so it's a ternary oxyacid. Then you go to your chart and you figure out, well, what is NO3? It's from NO3 minus, which is the nitrate ion. You're going to get rid of the ATE and write IC. And instead of ion, you write acid for nitric acid. If you have an acid that's derived from an oxyanion ending in ITE, then you change it to OUS, an acid. NO2 comes from nitrite, which is NO2 minus. So you get rid of the ITE and replace it with OUS. Replace ion with acid. Then you have nitrous acid. Here are some examples of ternary oxyacids. I'll draw your attention again to the hypo and us, per and ic. I'm not going to test you on those for the exam, and it's also not on your chapter check-in, but you may run into it for mastering chemistry. So make sure that you reference this chart and the polyatomic anion chart. It will have the per and the hypo and all of that on there, so you'll be able to answer those questions. But I'm not focusing on those. So let's practice naming ternary oxyacids. The first thing you're going to want to do once you've identified that it's a ternary oxyacid is identify the anion that it's derived from. ClO3 is the chlorate ion. The rules for 8 say that you get rid of the 8 and replace it with ic. And you always replace ion with acid, so that the name of this acid is chloric acid. Let's do that again. SO3. You look up what ion that is. That is the sulfite ion. For ITE, you get rid of that and replace it with OUS. You replace ion with acid, so that our name is sulfus acid. You may also see it written like this. They're the same. It's just a little spelling thing. This is Merca, so you're going to see it with an F. But if you see a PH instead, don't go crazy. It's okay. It's the same thing. That brings us to reminders. So, woo, you made it. Chapter 6. You have a Chapter 6 check-in and Mastering Chemistry Chapter 6 assignments due on Sunday, October 4th by 11:59 p.m. The chapter check-in is classifying 6 things. For 3 of them, you're going to write the name, and for 3 of them, you're going to write the chemical formula. So that'll be good practice. Then you have the Mastering Chemistry, which is the homework and the quiz. Your next exam will be available Wednesday, October 7th, and it covers chapters 5 and 6. Chapter 5 was the periodic table with the trends, noble gas configuration. We also talked about ions, and that led us into chapter 6, which we just covered, and that's the language of chemistry, classifying compounds, classifying ions, naming, and writing chemical formulas. So that exam 3 will be available Wednesday, October 7th through Friday, October 9th. That's all that I have for you guys. I'll be posting some practice for you, some worksheets that have a ton of practice for naming and writing chemical formulas. That is not going to be due. That's different from the chapter check-in. But if you need more help, I'm going to be pulling examples from there to do from class, but there are a lot of examples. So you can pull particular ones that you know you need help with, and you can go ahead and classify them too for extra practice. So I got your back. I'll give you plenty of practice, and you can always hit me up in office hours, which are officially Wednesdays from 2 to 4 p.m. If you cannot make that time, then you'll need to send me a message using Blackboard course messages and try to set something else up. I try to keep my meetings on Mondays and Wednesdays. Tuesdays I teach all the day, so ain't no time. But primarily, shoot for a Monday or a Wednesday, and I'll work with you. Alrighty, until I see you in class, stay safe.